Hi, and welcome to this fifth video lecture on the inverted pendulum and its dynamics. This is the inverted pendulum. We have a card of mass m uppercase, on top of which we have mounted a rod of mass m and length l. The reason why we study it, it's because we encounter it very often in engineering, like in robot walking, or segways, or even rocket launching. These are all examples, these are all cases of the inverted pendulum, or at least the dynamics is very similar. So what we'll do today here is that we'll use what we learned in all previous lectures, from the first to the fourth one. So we'll use what we learned about the state space representation and Newton's laws of motion and the rotational counterpart of Newton's second law of motion to derive the system dynamics of this system. And we'll start, as we always have to do, by introducing a frame of reference. This is our frame of reference, and since we have rotations, there are rotations involved, we have to define a positive direction for rotations, for angles. So we have here the angle theta, this is a positive angle. So without further ado, let's discuss about these points A and B. So point A is the fulcrum point, and point B is the center of mass. It is at the middle of the rod. Having introduced this frame of reference, just to practice a little, what are the coordinates of points A and B with respect to that? So XA is just some x, and YA, we just call x of A, we call it x. And YA is 0. We can move it wherever we like. We'll move it exactly here so that the altitude, so to speak, of point A is equal to 0. What about point B now? What is XB and YB? To answer that question, let us focus on this triangle between point A, point B, and the vertical line. So this is a right triangle. I know I'm at the end of the frame, I'm just trying to use the whole whiteboard today. So this is angle theta here. From A to B is just half of the length of the rod, so it is L half. And this side, which touches angle theta, is L half times cosine theta, whereas this side is L half sine theta. Now, XB, we can see this is equal to, recall that the x coordinate of A is x, and the y coordinate of A is 0. So the coordinate of this point is x plus this distance. And the coordinate of B, of this point, is 0 plus this distance. And all these xb and theta and yb are functions of t. So that was step number 1. To introduce a frame of reference. This is always step number 1 in all problems related to physics. What is now step number 2? We have two objects in our problem. We have the cart, we have the rod. To make our lives easier, we can study them and treat them separately. So we will start by studying the rod, for example. We'll take the rod. We will draw all forces that are applied on this rod. This is its midpoint, point B. This is the fulcrum point, point A. We will start by drawing all forces, and then we'll write down our equations. There are three forces acting on the rod. First is its weight, which is applied on the center of mass. Then we have a force coming from the cart, which props it up, supports it from below. And this is the vertical force N, points upwards. And then there is another force, we will denote it by H, as in horizontal. This is the horizontal force, which comes again from the cart. Since we apply a force on the cart so that we can push it to the right and to the left, this roughly speaking, pushes as well the rod. And this generates this horizontal force H. Again, the frame of reference is this one. Okay, so now we can employ Newton's second law of motion along the x-axis and then along the y-axis, of course, but let's start with the rod dynamics along the x-axis. The total force we have here is just H, nothing more. So H it is. And by Newton's second law of motion, we have this equation. Always, of course, with respect to the center of mass of the object, which is point B. Now, equivalently, let me just write this absolutely equivalently in the following form. Just to denote there that we have the second derivative of point xb. But point xb is given by this equation. Let's give them names. This is equation 1, this is equation 2. Therefore, it is the second derivative of this expression, where both x and theta are functions of time. Let us differentiate once, and then we'll do it once more afterwards. So what we did here is that we kept one derivative outside, and then we differentiated inside. The derivative of x is x dot. The derivative of this term, we have the sine of a function. The derivative of sine is the cosine, but we also have to multiply by the derivative of function theta. So it is cosine theta times theta dot. And now, let us differentiate once more. So we'll have this thing over here is the product of two functions. Let's say f times g. F times g. One function times another function. The derivative of a product is given by this formula. Derivative of the first one times the second plus the first times the derivative of the second one. So it is the derivative of cosine that one, times theta dot times the second, plus the first function times the derivative of the second one. And to simplify, so this is the first useful equation we have. The first differential equation we derived by taking Newton's second law of motion along the x direction. I will write it up there. I will collect here the useful equations. So I just copied the same equation up there. We'll do more, and the next one will be derived by taking Newton's second law of motion along the y direction for the rod once again. So I will create some space on the whiteboard. We don't need this any longer, it is up there. So along the y direction. So first of all, I moved L half outside, it is here, and now I'm going to differentiate cosine of theta once. So I keep one derivative outside and I'm differentiating cosine of theta. The derivative of cosine is minus sine, and now I will take the minus outside. And I will differentiate what is inside. Again, it is the derivative of a product of two functions, sine times theta dot. The same as we did before. For simplicity, I will multiply by minus 1 both sides of the equation. So I will have here and I will differentiate sorry, I differentiated it. I shouldn't have written that. So we differentiate that, and this is the result. And so this is the second useful equation. And the steps we followed were pretty much the same as before. So very similar procedure. And I will write it up there. Sorry about that. That's a mistake. So this is the equation. Great. Now we have used Newton's second law of motion along the x and the y axis, but we haven't said anything about the rotational dynamics of the rod. The rod can be seen to rotate around this end point A, but we can also take it to rotate around this point, point B, so it can be seen as, a rotation around its middle point. What are the torques that act with respect to middle point? We have a torque from N, which is a clockwise one, therefore positive, and we have a torque because of H, which is a counterclockwise one, therefore negative, according to this convention. So the torque of force N around point B is equal to N, the force, times the distance between the force and point B, which is that distance, the length of this line segment. So it is L half times sine theta. Just to make sure, the sign is positive because of that. Now, the torque of force H around point B is equal to minus this time, okay, H L half cosine theta, because now the distance between this force and this point is the length of this line segment here, which is L half times cosine theta. So the total torque and that we know from the rotational counterpart of Newton's second law of motion, we know that the total torque is equal to the moment of inertia with respect to point B times theta double dot. So let's write it. And the moment of inertia of the rod with respect to its middle point is exactly equal to 1/12 ml squared. I will divide both sides by L and multiply by 2, and the new equation we will have, and I will write it here, equation number 3, useful equation number 3 is the following. And now, regarding the rod, we have written down, I'm repeating, we have used Newton's second law of motion along the x-axis, Newton's law of motion along the y-axis, and we have also described the rotational dynamics around point B. We could have done it around point A, but it's slightly more difficult. So we chose the simplest possible path to discuss the system dynamics. There is one more equation which comes from the cart. We haven't said anything about the cart yet. So we have fully analyzed and discussed the dynamics of the rod. It remains to write down the forces for the cart and discuss its dynamics. So let me delete that. We have the cart, it is on the ground, it's on this surface, it has a mass m, therefore it has the weight m times g facing downwards. We said before that, actually I shouldn't have deleted that, we have the rod here, and we mentioned that there is a force N that props it up. This comes from the cart. If you think of it as an action, then there is a corresponding reaction, which is the force N prime that is applied from the rod to the cart. This force, because of Newton's third law of motion, of action and reaction, is equal to n in magnitude and has the opposite direction. So it's like that. And now, because of Newton's first law of motion, we know that this object doesn't move up or down along the y-axis. It has a zero velocity. Therefore, the sum of all forces must be equal to zero. There must be, therefore, a force R, which is a reaction coming from, it is an action coming from the ground, which just keeps everything there. Along the y-axis, everything equilibrates, and we have R minus N minus mg is equal to 0, which is a correct equation and can give us the magnitude of force R, but it's not really useful, so we don't need to write it up there in the list of useful equations. However, we need to write the system dynamics that comes from the study of this system along the x-axis. Along the x-axis, we have the force we mentioned before that we apply externally. This is how we can manipulate the system. This is our action, F. And we mentioned before that there is a force H because of the fact that we move the cart. So there is a force H induced by force F in some sense. Therefore, there is a reaction H prime which is equal to H by Newton's third law of motion, equal in magnitude, and they have opposite directions. We can simply write H here. These are equal forces in magnitude. So along the x-axis, the total force is F minus H. This is the system of reference. This is why it is F minus H. And F minus H is equal to, and this is the fourth useful equation. So now we have collected there 4 useful equations that describe the system dynamics, so there is nothing more we should do. Bye-bye. Oh no, wait, we're not over yet, because these 4 equations are nowhere close to a state space representation. So we're looking for something of the form x dot is a function f of x and u for some state vector x, and we would expect this state vector x underlined to involve, for example, variables x and theta, and perhaps their derivatives or something relevant. But now these equations involve h and n, which are, let's call them unwanted variables. We need to eliminate them out of these 4 equations. So we have 4 equations. We will eliminate the unwanted variables h and n, and we will end up with 2 equations that will involve only x, theta, and their second derivatives, and perhaps first derivatives, but only these terms, and constant parameters such as m, uppercase m, lowercase l, and the input variable f. That is to say, we will have an ordinary differential equation in the form we expect it to be, in the form we encountered in all other examples. This is a little particular an example. The exercise we're solving here is a little particular in that we have to eliminate these unwanted variables in the end. So let's do that. Let's do that. We'll start with the easiest one. Take equation A4. We can solve for h from there. Let's call this equation B1. Having done that, we can take h from here and we can plug it in equation A1. So instead of h there, we'll write f minus mx double dot, and we have In fact, this equation is a new useful equation because we have eliminated both n and h. So I will write it here. Here I will keep a list of the new equations. So the first one is this one. I will just copy it over here. And I have left enough space for the second equation we will come up with in a second. So for the second equation, let us observe equations a3 and a2. In a3 we have n times sine theta. In 2 we only have n, not n times sine theta. Ideally we would like to have either n in both equations or n times sine theta in both equations, so that we can solve one equation for, let's say, n sine theta, and we plug it into the other. But this can be taken care of very easily if we, for example, multiply both sides of a2 by sine theta. So let's take equation a2 and multiply by sine theta. We have so sine theta here, 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 and here in the form of a square, sine theta times sine theta. And we have n times sine theta in this new equation, which came from a2. And let's take n sine theta from a3 and plug it in here. So from a3, we have that n sine theta is great. So we have n sine theta here and here. Be careful with the signs when you do a lot of algebraic manipulations. And this is almost fine. It would be fine was it not for h that now shows up here. But we have an equation that gives us exactly h, and this is a1. So from a1 now, because of a1, we can write Now, this is what we were looking for, because it is an equation that only involves theta double dot, x double dot. In general, it only involves x and theta and constant parameters. But it's very lengthy and ugly, isn't it? And I promised you that there is enough space for us to write it here. So what about it? It's really ugly. By the way, h is that. I replaced h from a1, and we have that lengthy expression. But we can simplify it, and let's see how. First of all, we'll do all multiplications first we'll expand it to see clearly what terms we have. We can observe that some terms look similar, like here we have cosine, sine, and here we have cosine times sine, perhaps, something like that. But let's not jump into conclusions. Let's write out things like, let's expand the equation. So we multiplied here by cosine theta. We were very careful with the minus, so it is minus mx double dot. It is minus this term, and it is plus this term over here. We multiplied by cosine theta, so this term is this one, the square here, and this term over here. And now we can see clearly that we have L half sine theta cosine theta, theta dot squared, on both sides of the equation. This one is exactly the same as this one. So we can say bye-bye. We can bid them farewell. Okay, and we have one more interesting thing over here. We have, this is a little more difficult to observe, but we have that term with sine squared over there, and we have this term with cosine squared over here. Why are these terms interesting? Why do we need to club them together? Because of the property sine square of theta plus cosine squared of theta is equal to 1 for all theta. So if we move one of the terms on the other hand side, so for example if we move that on the other hand side, so I will delete it from here, we have a minus sign, so it goes to the right hand side with a plus. Then these two terms become right, and now we can write the remaining part of the equation. It can fit inside here because it's very small, but let's write it clearly one more time. So equivalently we have, can you see it there? Yeah. Too many m's. I can divide everything by m. I don't need the mass here. Now then, this equation is g sine theta so by eliminating h and n, we ended up with this pair of equations, which indeed involve only x double dot, theta double dot, and theta dot. So this is exactly what we were looking for. Let me create some space on the whiteboard. I will not do the rest now, but I will give you hints so that you can do it by yourselves. So this is a second order, this is a pair of second order differential equations. And we know, let's take the first one for example, that whenever we see x double dot, we have to introduce two new variables, x1 and x2. We know that x1 has to be equal to x and x2 has to be equal to x1 dot. In other words, x dot. And if we do that, then we have that x double dot is equal to x2 dot. This is for x. For x, we have two variables x1, x2, but we also have theta, and we have theta double dot as well as theta dot in these equations. We know then that we need to introduce two new variables. These will be, let's call them now x3, which will be theta, and x4, which will be x3 dot, or theta dot in other words. And then theta double dot is equal to x4 dot. We can now rewrite these two equations in terms of x1, x2, x3, x4. Let's do that very quickly. And it is natural to introduce the variable, the state variable x underlined, or however you want to call it, x1, x2, x3, x4, and f is the input variable, what we used to call u in previous lectures. So the input variable is equal to f. But we see here that everything is mixed up. Everything is a little entangled. So we have x4 dot here. We have x2 dot over here. They're like that. This is not good. We don't have a clear equation like x2 dot is equal to that, x4 dot is equal to something else. What do? we can observe that we have two equations with two variables, and the two equations are in fact linear equations. So we have a term times x2 dot, some other term times x4 dot, and so on, and we have a constant term. In terms of x2 dot and x4 dot, this is a linear system. We don't have any strange terms like x2 dot square root, x2 dot squared, or sine of x2 dot. We don't have anything like that. We have simple plain terms that involve x2 dot. It is something times x2 dot plus something else times x4 dot. This is a linear system in x2 dot, x4 dot. What I want you to do here is to solve this linear system for x2 dot, x4 dot. If you do that, you will end up with something like x2 dot equals something, which is a function of all other terms, but this is fine. It will be a nonlinear function of the other terms of x3, for example. You will have a sine x3 somewhere there, and the same for x4 dot. But at least what you will end up with will be the following, which is the desired result, will be x1 dot is equal to x2, x2 dot, the x2 dot solution from that linear system, whatever it is, x3 dot is equal to x4, and x4 dot is equal to the solution x4 dot from that linear system, which you will do as homework. x4 dot is whatever you will find. And the right hand side here will define the function f of x underlined and u, and we'll have the state space representation x underlined dot is a function f of x underlined and u. So again, as an overview, what we did, we started with this inverted pendulum system, which involves a cart of mass m and a rod of a particular length and given mass. We introduced a frame of reference. We studied the two objects, the rod and the cart, separately. In particular, we used Newton's second law of motion along the x and y directions for the rod, and we also used the rotational counterpart of Newton's second law of motion for the rod. We used only Newton's second law of motion along the x-axis for the cart. We didn't need to do anything more, and we ended up with these four equations. These are very good because they describe the system dynamics, but they're not good enough because they involve the unwanted terms h and n. Then, with some heavy and cumbersome and boring math, we were able to eliminate variables h and n. They were just lengthy, they weren't too difficult. And we have then these two equations. But these two equations form a linear system in, actually, I skipped a step. We introduced the auxiliary variables x1, x2, x3, x4, following what we learned in lecture number 1, and we repeated in lecture number 2. And then we ended up with this linear system. Now, if you solve this linear system, you will be able to recover the state space representation for this system. So that's it for today. Thank you very much for watching, and until next time, goodbye.